Let's say you're standing on the top of an elevator shaft and you don't know the height of it. So you drop a basketball, assume that basketball is in free fall, and count about 3 seconds until the ball hits the bottom of the elevator shaft. About how tall is the elevator shaft? Here's a sketch of this very tall elevator shaft. Here, let's zoom. Right, we're given only one number in the entire problem, and that's 3 seconds. I recommend that after you make a sketch of the situation, we write down everything that we know about this problem. So we know the time of this drop is 3 seconds. We know that this is a case of free fall, so we're going to get to assume the acceleration due to gravity. Now, it's 9.8 meters per second downwards. That means now it's time for us to assume something about a coordinate system. So I'm going to call the ball's drop height 0 meters, and I'm going to say that downwards is positive. This will make it a little easier when working with some numbers later on. So downwards is positive. That means the acceleration, which is also down, is also positive. That's a little different than kind of the convention that we've seen in some previous problems, but that really is your choice. Okay, next step. Have we written down everything we know? Oh, wait. There's one more bit of information we don't know. Initial velocity. The word drop is an important key word for us to recognize. Drop means that dropped from rest as opposed to thrown downwards. Initial velocity is 0. We're being asked for how tall the elevator shaft is. So that's a height here. But we don't have anything under free fall that uses the letter H for height. So I'm just going to rename this variable, the height of the elevator shaft, as the displacement of the ball. How come? Well, the ball starts here at a height of 0 meters, and it's going to fall to here at some other height. Now, because downward is positive, this is going to reach some large positive height. And so that height of the drop is the same as the displacement of the ball. All right, so we're solving for displacement. Once you've written down everything you know and you've anchored it on a diagram, now it's time to start solving. I recommend start with a position time and maybe a velocity time graph. We're starting at a height of 0 and we're moving downwards while speeding up. So you might have something like this. And maybe on a velocity time graph, we start at 0 and we increase velocity linearly. That may not look like much of a straight line, but it's supposed to be. Okay, how tall is the elevator shaft? I could find the area of this triangle if I knew how much time. Oh, well, it takes 3 seconds. If I knew how fast the ball was going at the bottom of the shaft, I could solve that way. Let's see. Can I find final velocity? Oh, yeah, actually, the equation on this graph of the line is this. Totally forgot to bring my calculator. Pardon me while I do it on screen. 9.8 times 3 is 29.4 meters per second. But I'm not being asked how fast the ball's going when it hits the ground. I'm being asked for displacement. So if I want to do displacement area of that triangle, doing it again on the computer, that is 44.1 meters. That's way 1 to go about this problem. Way 2 is maybe a little more direct. It uses purely one algebraic equation. It's the equation of this curve. Delta x, which is what I'm looking for, is not quite the same as x or x initial. It's the difference between them. So I know all these numbers. The initial velocity is 0, the time is 3. That first term goes to 0, 1/2 of 9.8 times 3 squared. How tall is the elevator shaft? The answer is 44.1 meters. We see here now there's 2 ways you might go about solving this problem. Method 1, using leaning more heavily on the graphs over here. And method 2, leaning more heavily on a single algebraic equation. I honestly encourage you to try solving problems both ways. You better wind up at the same result because how tall is the elevator shaft? There's only one possible answer here that's correct. Best of luck as you work other problems like these.